In this video, we'll be discussing question 1 to question 3 of question paper 4.1 and 4.3 of the 9701 chemistry examination series, May-June 2024. And so let's start with question 1 now. And the first question says, describe the trend in the solubility of the hydroxides of magnesium, calcium and strontium and explain your answer. So now if you talk about magnesium, calcium and strontium, they are group 2 elements with magnesium on the top, then comes calcium and then comes strontium. So going down the group, the cation size increases, we know, and going down the group, the solubility of hydroxides of group 2 elements increases. So that's why strontium hydroxide is more soluble, and so let's write here starting with strontium, then calcium and magnesium. That's how it works. Magnesium hydroxide is least soluble in all these three elements, and the reason being is that we need to start right from the first part, that is going down the group, group 2 cation size increases because magnesium hydroxide or to strontium or calcium hydroxide, the element is in cation form in +2 form. So we can write that cation size increases, and hence the delta H lattice, that is enthalpy of lattice and enthalpy of hydration, both becomes less exothermic, or you can even write that it decreases in value. So it becomes less exothermic, but enthalpy of lattice, that is lattice energy, decreases by greater value, that is becomes more or less exothermic. Also you can say decreases by greater value. Hence delta H solution, that is enthalpy of solution, becomes more exothermic, and if enthalpy of solution becomes more exothermic, solubility increases. That means that more the value of delta H solution, enthalpy of solution negative, more the negative value, more will be the solubility, and hence enthalpy of solution becomes more exothermic, the solubility increases. That's how we can write. Because it's 4 mark, we need to describe it in detail with 3 to 4 minimum points. Okay, let's see what's the next part. It suggests the variation in the pH of the saturated solution of hydroxides of magnesium, calcium and strontium. So we can say that the pH of strontium hydroxide is greater. So we can write that the pH of strontium hydroxide is highest, as the concentration of OH minus increases, and the reason is that the solubility increases and hence the OH minus concentration increases, and hence the pH value also increases. Now let's go ahead with the next part, where B part, it says that barium hydroxide, that is BaOH twice, is a strong base. A 250 cm³ solution of barium hydroxide with a pH of 12.2 is made by dissolving barium hydroxide in distilled water. Now understand, we are taking 250 cm³ of solution, we are making it by dissolving barium hydroxide solid in the water. Calculate the mass of barium hydroxide required to make this solution with a pH 12.2 and show your working. And here the relative molecular mass of barium hydroxide that is given is 171.3. So if the pH is given, the first thing what we can do is calculate the concentration of H plus by the formula of H plus is equal to 10 to the power of pH, that is 12.2, which is equal to 6.31 into 10 power minus 13. Okay, now but we are dealing with hydroxide and not the hydrogen ion concentration. So from this we need to find out the concentration of hydroxide ion, which is related with this equation. Now this equation is called the ionic product of water, and the value of Kw is equal to 1 into 10 power minus 14. Now we know the value of H plus also, that is 6.31 into 10 power minus 13 into hydroxide is equal to 1 into 10 power minus 14. This gives us the value of hydroxide concentration by dividing 1 into 10 power minus 14 divided by 6.31 into 10 power minus 13, and we get the value as 0.0158 moles per dm cube. And we need to write the concentration unit, that is hydroxide concentration, into moles per dm cube. Now understand this hydroxide value is 0.0158 moles per dm cube. Now this is per dm cube, but we need to find out for 250 centimeter cube. And another point is that when barium hydroxide dissolves in water, it ionizes into Ba2 plus and 2 hydroxide ions moles ratio. So if we are talking about hydroxide ions concentration, the concentration of barium hydroxide solid will be half of it. So if we want to find out the concentration of barium hydroxide, we need to divide the concentration of hydroxide by 2, because there is 1:2 ratio. So from this we definitely can calculate the barium hydroxide concentration, that is 0.0158 divided by 2. Also remember, this is concentration per dm cube. Now if you want to find out the moles of barium hydroxide in 250 centimeter cube, we also need to divide it by 4. So we are doing it all together. So let me write here moles of barium hydroxide, and this gives us the value as 1.98 into 10 power minus 3. Now these are the moles. What we did is first find out the concentration of hydroxide ion. From that we found out the concentration of barium hydroxide by dividing it by 2. Now if we want to find out the moles in 250 centimeter cube, we'll divide that moles by 4, because the moles which were there were for 1 dm cube. Now we want to find out it for 250 centimeter cube, so it's 1/4 ratio. 1 dm cube is 1000 centimeter cube. We need to find out it for 250 centimeter cube, that is 1:4 ratio. So divided by 4. So these are the moles of barium hydroxide. Now from this, if we want to calculate the mass, then simple calculation is mass is equal to moles into mr. So now we can multiply 1.98 into 10 power minus 3, and the mr 171 is given 171.3. So this is how we calculate the mass, which is 0.339 gram. Okay, so here we got the answer. Let's go ahead with the next part. Okay, the solubility of iron 2 hydroxide, that is FeOH twice, is 5.85 into 10 power minus 6 moles per dm cube at 298 Kelvin, and the solubility product expression we need to write. Now first, here it's written calculate the KSP of FeOH twice, include its unit also. So let me write the expression here as ionic equation as Fe2 plus 2OH minus. This is how we write the ionizing ionic equation of FeOH twice. Then in that case we can see that here the ratio is 1:1, and from here to here there is a ratio of 2, 1:2. Hydroxides are 2. So if we write the ionic KSP expression, it should be Fe2H and OH minus power 2. Why? Because this 2 will go in the power. So this is how we write the KSP expression. Now it's also written, calculate the value of Ksp for FeOH twice, where the solubility of ferrous hydroxide is given, that is 5.85. So if I write 5.85 into 10 power minus 6 here, we can see that these are the moles which will dissolve. It will give ion Fe2 plus also in the same ratio, that is F 5.85 into 10 power minus 6. But the hydroxide ions produced will be double, that is twice. So 5.85 into 10 power minus 6 multiplied by 2 should be the value for the moles of hydroxide produced, and this is how we'll substitute it in the Ksp expression. So Ksp is equal to Fe2 plus concentration, that is 5.85 into 10 power minus 6, and the concentration of OH twice is 5.85 into 10 power minus 6, also multiply by 2, and that also should be square. This is how we write. So 2 square is 4 into we can write 5.85 into 10 power minus 6 square we can write. This is how we can simplify writing it. You can directly do it in the calculator also. Okay, sorry, my mistake. This is already square, and one more time we multiply, that's cube. So 5.85 into 10 power minus 6 cube it will be. And now let's calculate, and the value is 8.01 into 10 power minus 16. So the value is 8.01 into 10 power minus 16. Now what about the units? Now you can see that we have taken the concentration thrice, that is once and twice here because of the square here. So in that case the unit will become mole power cube and dm power minus 9. dm power minus 9. So that's the unit because it's thrice. Let's go ahead with the second question. Here it says define transition element. Define transition element. Simplest definition which we can write in 1 mark is the element which has one or more stable ions with incompletely filled d orbitals. That shows that the ions should have incompletely filled d orbitals, not the elements. So it should have one or more than one stable ions with incompletely filled d orbital. Then the element is called transition element. Now explain why transition elements can form complex ions. Simple, that its d orbitals are vacant. So d orbitals are available easily for the other electrons to be occupied, it. So this is why the complex ions are formed, because d orbitals are available, so the electrons from the ligands can occupy these d orbitals and can form complex ions. We can also specify it that the electrons from the ligands can occupy this d orbital available, but as it's only 1 mark and we are having only 2 lines, we can shorten it writing like this. The 3 d orbitals in an isolated Ag plus ion are degenerate. Now define degenerate d orbitals. Degenerate d orbitals are, now it's clearly written isolated. Isolated means not bonded with ligands. So if it is not bonded with ligands, the d orbitals are degenerate. That shows that the d orbitals have same energy. That is, all the 5 d orbitals have the same energy. Then we call it as degenerate d orbitals. If the orbitals split into 2 different energy levels, then we call it as non-degenerate orbitals. Okay. Next part, sketch the shape of 3D XY orbital in figure 2.1. 3D XY it is. So D orbitals, we need to remember there should be two dumbbells between the X and Y axis. So here are the X and Y axis, and the two dumbbells between the X and Y orbitals. I'm not able to draw because it's a digital pen, digital screen, but you can draw it with pencil properly in your papers. Okay, the next part says the tolerance reagent can be used to distinguish between aldehydes and ketones. Now, what is a tolerance reagent? It contains the silver ions in this complex form, which can be prepared in a two-step process. Now, what's that process? It says step 1, aqueous NaOH is added dropwise to AgNO3 to form Ag2O, that is silver oxide as a brown precipitate. And the step 2, aqueous ammonia is added dropwise to the silver oxide to form a colorless solution containing this complex. And this is how the complex is prepared. Now, construct equations for each of the steps in the preparation of the silver complex. Now, if we talk about the first step, what's written there is NaOH is added to AgNO3, and if we are supposed to construct equation, let's start with AgNO3, that is silver nitrate, where NaOH is, that is sodium hydroxide, is added, and what is formed is silver oxide. The formula is given here, silver oxide is prepared. Now let's have a look at this equation, that if we have already used silver and oxygen to form silver oxide, what are we left with? We are left with hydrogen, we are left with nitrate, and we are left with sodium. So obviously the byproducts will be silver nitrate, and where will the hydrogen go? It will form water. Now let's balance it. If it is here, silver oxide is Ag2O, we need to add 2 here to balance it, and obviously then we need to add 2 here also and here also, and now it's balanced. You can definitely pause and count the number of hydrogen, oxygen and all other elements, and you will feel that it's balanced. Now let's go ahead with the step 2, where it says that ammonia is added to silver oxide to form the colorless solution. So if we are adding silver oxide and ammonia is added dropwise, and the complex formed is AgNH3 twice OH. Now if we balance it, we can see that here we have to add 2 because the silver are 2 atoms on the reactant side. Now the ammonia becomes then 2 into 2, that is 4 times, we add 4 times. But then now what about OH? Where has this OH come from? So for to balance, we need to add water on the reactant side, and the reason being is that it's aqueous ammonia added dropwise, and from there we got the OH, and otherwise our equation won't get balanced also. So now if you check all the balancing part, it's fully done. That is, water is added on the reactant side, from where we get the OH, that is hydroxide, and that's how we get the complex. Okay, next part, need the shape of the complex ion, that is silver ammonical twice, that is Ag plus. State the bond angle of H and Ag and NAgN shape. Okay, so if we talk about this shape, it's like simple, where Ag is in the plus form and there is an ammonia. Sorry, I'll draw it this way. There is ammonia on both sides, and obviously the shape is then linear because there are only 2 ligands bonded to the silver ion, which is at the center. Now if we talk about the bond angle of H and Ag, now H and Ag, that is ammonia and Ag. Now if we know that ammonia is like trigonal pyramidal NH3, and then that is bonded to Ag, and we need to find out H and Ag is this bond angle. Now ammonia in normal way is trigonal pyramidal with 107 degrees, but if the lone pair which was there on the nitrogen is donated to silver ion to form the 4th bond, then without any lone pair left, all there are 4 bonding pairs, then it changes its shape to tetrahedral. Now the shaped tetrahedral have an angle of 109.5, that we know. So H and AG shape bond angle will be 109.5. If we talk about the bond angle NAGN, that is the straight way, NAGN, that's linear shape. So we know the bond angle is 180 degrees. The next part E, it says an electrochemical cell uses silver oxide as the positive electrode and zinc as the negative electrode immersed in an alkaline electrolyte, and the overall cell reaction is given here. Complete the half equations for the reactions at each electrode. Now we need to know that the silver Ag2O is a positive electron, and in an electrochemical cell the positive electrode is the one which gains electrons. So for sure we need to add electrons here, and we also need to know that silver oxide is having Ag plus, that is silver is present in the form of Ag plus. Now if there are two Ag ions, then it should gain 2 electrons. So by balance we need to add 2 electrons here. After gaining 2 electrons, it's forming for sure 2 Ag, right? Yeah, 2 Ag is formed. Now let's see what else, because there is one more oxygen to be balanced here. But let's see what is a negative electrode. Now negative electrode, we know that zinc is a negative electrode, and electrochemical cell zinc negative electrode always loses the electrons. And we can see that the product is zinc hydroxide. The product is always going to be zinc hydroxide, and it's going to lose the electrons. Obviously Zn2 plus is formed, so it's going to lose 2 electrons because 2 plus is formed. Now what about OH minus? Where did it come from? So we need to add 2 OH minus as an ionic equation with zinc to form zinc hydroxide, and 2 electrons are formed. Now obviously if that is 2 hydroxides are formed, and it's written that it's an alkaline electrolyte. So if 2 OH minus are used up at the negative electrode, that should be formed as at positive electrode, and because of that we need to add water here, because we can see that 2 Ag plus is formed and hydroxide is also formed. Where has that hydroxide come from? The oxygen and the water. Okay, so O is here, and one more reactant water is present here, that's going to react at the positive electrode with the silver oxide to form silver and hydroxide. That hydroxide in the alkaline electrolyte is going to react with the zinc to form zinc hydroxide and losing 2 electrons. Remember, in electrochemical cell, negative electrode loses electrons and positive electrode gains the electrons. Okay, let's see the next part. Next part is coordination polymers are made when a bidentate ligand acts as a bridge between different metal ions. Under certain conditions, Ru3 plus, that is ruthenium 3 plus, and the bidentate ligand DPS. Now DPS is given here. This is the whole structure given, where a hexagonal ring with the nitrogen in between is formed with the sulfur bridging between it. It can form a coordination polymer containing ruthenium DPS, Cl4 charge minus N and chains. So you can understand that's a polymer where one of the monomer is going to keep on getting repeated again and again. Now let's understand what is all this about. The bidentate ligand DPS uses each of its nitrogen atoms to bond with different ruthenium ion. Now different, not the same. Understand that. So if one of the Ru3 plus is bonded to one of the nitrogen, the different ruthenium ion is going to bond with the another nitrogen of the same ligand. Complete figure 2.3 by drawing the structure of the coordination polymer. Understand that's a polymer. Show 2 repeat units, and DPS can be presented by this way. Okay. So if ruthenium is this, and if the ligand is going to bond this way nitrogen, obviously this is ruthenium again, and the next ligands should be bonding this way on the another part. So you can understand that this nitrogen is bonded to another ruthenium, thus nitrogen is bonded to the second ruthenium complex, again a nitrogen, and this way it continues. So here if we draw, then we know the complex has also got Cl4, so the remaining 4 bonds has to be occupied by chlorine ions. So chlorine is shown here, same way it should be drawing this way. So chlorine here, here, here and here. So this is how we draw the 2 repeat units. Now if I have drawn nitrogen here, it's okay if you don't draw the nitrogen here and draw an extended bond this way, and this is how we complete the 2 repeat units. So fine, the structure is drawn here. Let's go ahead with the question 3, where it says when a sample of hydrated lithium ethane diet, and the formula is given here, is gently heated, 2 gaseous products are formed and a white solid residue remains. Okay, understand there are 2 gaseous products formed. Fine. The residue is added to nitric acid, a gas is produced that turns lime water milky. So reacting with nitric acid is going to produce carbon dioxide, and this we are talking about the residue which is produced by heating this hydrated lithium ethane diet. That shows that the lithium carbonate is definitely formed as a white residue which reacts with an acid to produce carbon dioxide gas. So we know now for sure that lithium carbonate is produced. So it's written, complete the equation for the decomposition of hydrated lithium ethane diet. Okay. So lithium carbonate for sure is one compound, we have come to know. Okay, and any ethane diet on heating, that's hydrated. Remember, this is hydrated. So obviously if we heat it first gently and then more, we release out the water molecules of the hydrated compound. So again, one of the compound is definitely water. Now what are you left with? Let's count. Let's count how many elements are we left with. Lithium 2 we have used up. Water is already gone. Out of C2O4, 1 carbon and 3 oxygen are used. So we are left with only 1 carbon and 1 oxygen, that is carbon monoxide. That's how we balance it. So there are 2 gaseous compounds, 2 gaseous products formed, that is water and carbon monoxide, and lithium carbonate as one of the solid white residue remains is formed. Okay, next part is B. The trend in the decomposition temperatures of group 2 ethane diets is similar to that of the group 2 nitrates. Suggest which of these, calcium ethane diet or barium ethane diet, will decompose at a lower temperature, and explain your answer. Now we know the trend that going down the group, the decomposition temperature of group 2 nitrates increases. That is, barium compounds should have a higher temperature required to decompose. So what's the lower temperature one? Calcium ethane diet is decomposing with the lower temperature. So will decompose at a lower temperature, Fine. Explain your answer. Again, we can write that going down the group, cation size increases, this decreases the polarization. So polarization decreases, or you can also write the reverse. Going up the group, the cation size decreases, hence the polarization increases. You can write the same way also, and hence the CO bond gets stronger. and so temperature increases down the group and hence the temperature decreases up the group, and that's why the calcium ethane diet will decompose at a lower temperature. Okay, let's see what's the next part. It says that potassium iron 3 ethane diode dissolves in water to form a green solution. Explain why transition elements can form colored complexes. Obviously, iron 3 is a transition element, and because of its presence, it forms a green solution which is colored. And we need to explain why transition element forms colored complexes. So the simple reason is that the transition elements have non-degenerate orbitals, d orbitals. I'll specify orbitals when it bonds with ligands. When white light is passed through the solution, of complex, the electrons from lower d orbitals jumps or gets promoted, also you can write jumps from lower to higher d orbitals, absorbing some part of the wavelength, absorbing some part of the wavelength of white light. Okay, the part of light transmitted gives color to the solution, This is how we'll describe. Actually, it's a very lengthy description for 3 marks, but as we had the space, I won't skip any part of the description and I'll describe everything. That's how I prefer for any question. So next part, it says the anhydrous iron 3 compound of this given complex decomposes on heating to form a mixture of all this. It's written here, complete the equation of decomposition of all these equations. Fine. Here it's K3Fe, it's the complex solution given, and these products are also given, and we need to balance it. Now the first thing is that then ethane diode is thrice here, and it splits into 2 and 1 here, and the potassium is 3 here and it splits into 2 and 2. Obviously it's not balanced, but to balance, the only solution is that we can keep 2 here. So now the potassium gets 2 into 3, that is 6, and the ethane diode ion, which is thrice here, again multiplying, becomes 6 here. So here we have 2 and 1 ethane diode is here. So if we balance it with this, we get potassium 4 here and 2 here, that gets 6. Ethane diode ions, that is again 6 ions, will get balanced with 2 and 2 4 here, and with 1 5 here, and then CO2 is also released where the carbon is totaling into 6. So now if we want to total the carbon to 6, that is 2 into 3 6, 6 into again 2. So if we talk about the ethane diode ion, we are already done with 2 into 2 4, 4 applies to 6, 6 we have already done, multiplying again with 2, that is 2 into 2 4, 4 into 2 8, 8 carbon is already done, plus 2 we are already done, and we are left with 2 more. So to balance, we can keep 2 here. Now if we count all the potassium, ethane diet and iron, it's all balanced, so only one required here. So this is how I have balanced. I have counted potassium, I have counted iron, I have counted the ethane diet ions with carbon I have counted, and then I counted the carbon dioxide left over. Fine, now it's balanced here. Okay, let's go ahead with the next part, where again an iron complex is formed again with the ethane diet ion. It shows a stereoisomerism. Okay, complete the three-dimensional diagram in figure 3.1 to show the two stereoisomers of the iron ethane diet complex. C2O4 2-, that is ethane diet ion, can be represented as this, because again it's a bidentate ligand. We know that it's a bidentate ligand, and it can be represented as shown here. So now if it is twice, we know that the coordination number of Fe should be 6. Then only the bidentate ligand can be 3 present on the iron complex. So if we are told to draw the three-dimensional diagram, I'll add 4 more bonds with the dotted lines and the bold lines, because this is how we present the three-dimensional diagram of an octahedral complex, where 2 bonds are away from us, 2 bonds are towards us, and the 2 other bonds are in the same plane, and there are 3 ethane diet ions presented by O. So I'll draw it this way. Okay, done. Yes, it's done. One of the complex is done. Now the isomer has to be the mirror image of this. So I'm drawing again with the same part. Okay, 2 bold lines, 2 dotted lines, and the mirror image of this has to be this way, exactly the mirror image. Yes, it's done. So draw it. You can again replace the position of this ethane diet this way, that is fine, but the second isomer should be the mirror image. That's the main part you should be taking care. Okay, buffer solutions are used to regulate the pH. Write 2 equations to describe how a solution containing the ethane diet ion, that is HC2O4- ion, acts as a buffer solutions when Okay, so the next part F is buffer solutions are used to regulate the pH. Write 2 equations to describe how the solution containing HC2O4- ion acts as a buffer solution when small amounts of acid or alkali are added. So acids are H plus and alkalis are OH-. They are added to the HC2O4- ions to regulate the pH. So this is how we are going to write the equations. Now the main part is that how are we going to write the product. So if H plus is added, we can directly see that it neutralizes with the charge, and so it turns to H2C2O4. That's how it does, because one of it is negative, one of it is positive, gets neutralized to form H2C2O4 as a product. But yes, if it reacts with the alkali, it's going to form water as one of the product. And so if we find out water, whatever you are left with is C2O4-2-. Okay, so this is how you're going to frame an equation for the buffer working. Fine. The next part is a fuel cell is an electrochemical cell that can be used to generate electrical energy by using oxygen to oxidize a fuel. Okay, ethane acid dissolved in an alkaline electrolyte is being investigated as a fuel, and the relevant standard electrode potentials for the shell are shown here with the 2 equations. The values are also given. Okay, so going ahead, use these equations to deduce the overall cell reaction, calculate the E cell value also. Now looking at this, we can see that the second equation has a negative value, and generally the negative value goes the reverse side. That is, the product is the reactant here and the reactant is the product here. Now if we look at the electron number, There's a 4 electrons in the first half equation, and the second equation also have 2 electrons. Now if we want to balance the electrons, we need to multiply this equation with 2. So starting with that, if we reverse it, we write C2O4 2 minus. That will give 4 CO2 and 4 electrons, and if we add the first electron as such in the same way, we get O2 plus 2H2O plus 4 electrons, and that gives 4OH minus. Now the electrons gets cancelled and the remaining part you can add as such. Okay, so let's write it on finally on the lines where we will write adding up both the equations together with the reactant part together and the product part on the other side, and this is how our whole ionic equation gets completed. Now if we want to calculate the E cell value, we need to understand that the equation which is reversed, we need to change its sign, and the one which is forward has to be written as such, and then we add it. So this is how we add, by reversing the sign of the reverse equation. Okay, so minus 0.59 becomes positive 0.59, and then we add it, and so we get a 0.99 as the volt. 0.99 is the voltage, as 0.99 voltage, fine here. And we can see that the question 3 also gets over. I hope all the question 3s are clear with the explanations given here. In the next video, we'll be again discussing the next 3 questions.